In the last video, we talked about the magnetic flux in terms of the B field and the area of some loop. Now, for our purposes, we're going to, from henceforth, consider that this loop is some sort of conducting material. Probably it's just a wire that I bent into the shape of in this case, a circle, but it doesn't have to be a circle. It's got some sort of area, but I bent it and I attached the ends and so that it forms a closed loop. So, and I can define the magnetic flux like this. What I want to try to convince you of course, is that the magnetic flux can be a function of time. That is, it can change in real time. We talked about reorienting this loop, reorienting the vector in different ways. Well, what if this is connected to something that's making it rotate? Then the flux is changing in time. If this thing is rotating, the flux is constantly changing. I could even construct something where the area of this is shrinking or getting bigger. If I have a wire, which is kinked, and I pull on the ends of this wire, then that area gets smaller. If I push on them, that area gets bigger. So there are all sorts of different ways that I could change the flux in time. Of course, I don't have to change it, but I can change the flux in time. When I do that, something really, really interesting happens. So let me first talk about how to write that down. For change, we're just going to use our good old delta. Change in the magnetic flux. And what I said is it can change in time. So let's just form this. Delta phi sub b over delta t. This is our good old change in time. We've seen this since time immemorial, basically. We had, the change in position per unit time led us to a speed. The change in velocity per unit time led us to an acceleration a long time ago when we were in physics 1. But so this is just a pretty standard way of analyzing a system. If this is changing in time, one of the ways to do that is to determine how it changes and divide that by the time it took to make the change. But when I do this quantity, and I'll just have to ask you to trust me. I'm not gonna, you're welcome to get in here and show. But if I just look at the units here, interestingly enough, I get units of volts. What is a volt? It is a unit of electric potential. We normally encounter those with batteries. That's really interesting, and that can't be an accident. It has to mean something because that's how physics and the physical universe work. And as it turns out, this is exactly what happens. If I take a loop of conducting material and I change the magnetic flux through that conducting material, what I get is an EMF induced in the wire, which causes a current to flow. So let me show you what I mean. Let me draw a loop here. I'm going to leave a little gap so I can draw something else, but don't imagine that there's actually a gap. Imagine that this is connected. And then I'm going to put a magnetic flux through this loop, and I'm going to change it. How do I change it? That's up to me. I could change the magnetic field, right? I could turn down my magnets if they're electromagnets. I could change the orientation of the wire and the field. I could either rotate the wire or rotate the field. I could make the field get stronger or weaker. I could do any number of things. But if I change the flux, what happens in the wire is that a little EMF is induced. Now, does a battery magically appear in the wire? No. But that's the idea. I induce some EMF. This is a closed loop. If you induce an EMF across 2 points in the loop, guess what's going to happen? Current is going to flow. And the way I've drawn the EMF, current will flow in this direction. That's really interesting. Although if you've ever used a generator, this is exactly what's happening. A generator consists of coils of wire interacting with a magnetic field, and somehow you are changing the flux through that wire. Most often, you're making this thing turn by connecting it to probably an internal combustion engine. If you've ever seen the portable generators where they have pull starts like lawnmowers, that's what's happening. You're turning a coil of wire inside a magnetic field, thereby changing the flux and producing electricity. This actually turns out to be phenomenally useful for the human race. In fact, with the exception of solar power and geothermal power, at some point, pretty much every bit of electricity that we use as a species comes from this somehow. Like I said, solar is the exception, geothermal is an exception. There are a couple others, but all power plants use this method. The difference is in how they make the thing turn. Hydroelectric power uses water to make a coil turn inside a magnetic field. Wind power uses wind to make a coil turn. Coal-fired, wood-fired, nuclear power plants, all of those boil water, which turns a big turbine, turns coils inside a magnetic field, and makes electricity. So interestingly enough, the change in magnetic flux, if there's a change in magnetic flux through a loop of conducting material, you induce an EMF, thereby causing current to flow if it's able. So let's write down what we actually know here. I'm going to write this. The EMF induced in any coil of wire is equal to this, negative, and I'm going to write an N here. We'll talk about that in a second. And then the change in flux per unit time. So my flux is changing per unit time, induces an EMF. We'll talk about the negative sign also. This is just a recognition or a recognizance that I can have more than one loop here. The number of loops, some people will say the number of turns, because as it turns out what happens is they make coils of wire and they call the number of loops the number of turns. So if in this case N is 1 because there's only one here, but if I were to stack 5 of these on top of each other, then N would be 5 and I'd have to multiply the whole thing by 5, right? That's just what that is. Now the negative sign, we got to deal with the negative sign. So we know that negative voltages, negative potentials are no big deal. But what this tells you in this case is that the EMF will be induced such that nature tries to counteract the change in flux. This is definitely not a physical law, but it's a good guiding principle for dealing with stuff like this. The idea that nature hates change. In some cases, of course, that's definitely not the case. In some cases, nature embraces change. Although I should point out I'm anthropomorphizing nature, and that's usually a bad idea. But just go with it. As long as you understand that I don't actually think nature is sentient. But we saw this in mechanics. Newton's first law. If you don't do anything to a system, it keeps doing exactly what it's going to do. Right? It keeps doing exactly what it's doing. You have to go in and change it. This is all over physics. Nature hates change. And so nature does not like the fact that there is a change in flux here. So she tries to counteract it. How does she try to counteract it? Well, recall that when a current flows, that current produces a magnetic field. And so you have two magnetic fields occurring here. You have the background magnetic field, the external, and you have a magnetic field that is produced by this current. The magnetic field produced by the current is passing through the coil, therefore it contributes to the flux. And so nature induces a current such that the magnetic flux, due to the current, tries to stop the change. What does that mean? Let's write down the options, because I think this is a handy exercise. Write down what that can mean and what that can mean and how to analyze it. So what that means, I'll put that here. If the flux is increasing, nature tries to decrease it. If the flux is decreasing, nature tries to increase it. Let's give a simple example here. Let me take a loop of wire and let me pass through that wire a magnetic field. And I am going to change the magnetic field. I'm going to change the strength of the magnetic field, and I'm going to let it increase. So the wire is not changing, the orientation is not changing. I could do that if I wanted to, but I'm just going to let the magnetic field increase. Therefore, the flux is increasing, right? If the magnetic field is increasing but nothing else is staying the same, if I remember the definition of flux, let me write that over here. It's B A cosine theta, right? There you have it. B is not changing, A is not changing, cosine, B is changing, A is not changing, cosine theta is not changing. And so what I have here is the situation where the flux is increasing. Now, if I know the area of this and I know how the B field is changing in time, I can come up with a number for the induced EMF, no big deal. The more interesting thing is to ask ourselves, which way does the current flow in order to counteract the change in flux? So think about it. And this is critical. You got to go through these thinking steps here. The magnetic field is pointed to the right and it's increasing. Nature wants to decrease it. Nature hates the change. So if the flux is increasing, nature wants to decrease it. The flux is coming from the field to the right. Nature wants to decrease it. So nature has to induce a field that will decrease the flux. What does that have to look like? It has to look like, I should do this in a different color. It has to look like this, right? This has to be the B field from the loop. Nature has to induce it like this because nature wants to decrease it. So how does the current flow? To do that, I've got a field and a current. I need to use my right-hand rules for fields. Remember, I put my thumb in the direction of whatever's straight. In that case, this is the B field. My fingers then will tell me the direction of current flow. So the B field looks like this. I put my fingers in the direction of current like that, which means that this is flowing like this. To make it a little bit more explicit, up here, the current is flowing into the page. Down here, the current is flowing out of the page. It's forming a loop. So let me go through those steps again. I figure out if the flux is increasing or decreasing. I told you it was increasing. Then I ask myself, what does nature want to do? Well, if the flux is increasing, nature wants to decrease it. How do I decrease the flux from this field? I've got to induce an oppositely directed field. That looks like this. Now I use my right-hand rule to tell me the direction of the current that will produce this field. So the current's flowing because the change in flux induces the current. The current is in this direction because it induces a magnetic field to counteract the change in flux. Okay, it's a few steps away, but it's okay. It just takes a little practice. Let's do another one. Let's see what happens here. So I'm in the same situation. There's my loop. Here's my magnetic field. Same direction, everything. Okay. But this time I'm going to tell you that I'm turning down the field. It's getting weaker in time. So we're going to go through the same steps. We're going to ask ourselves, is the flux increasing or decreasing? Well, if the field is decreasing and nothing else is changing, then the flux is decreasing. What does nature want to do? Nature wants to increase the flux now because it hates change. So if it's decreasing, she wants to increase it. How can she increase the flux through this? She's got to induce a field that looks like this. So here is B of the loop. How do we induce get a magnetic field that looks like this? We've got to let a current run this way. Put my thumb in the direction of what's straight. The current will now run this way. To be really explicit, up here it comes out of the page. Down here it comes into the page. You can usually write that like this and we'll know what you're talking about. But the direction has changed. Notice the direction of the current is different now. It's got to be different because I need to induce a field in the opposite direction. Okay, those are just two ways that I can do this. There are other ways which we'll see in examples we go through in class. There are also examples in your book. This whole loose collection of guidelines is usually called Lenz's law. Lenz's law is basically the steps we just went through for determining the direction of the current. Like I say, usually finding the magnitude of the EMF is not that big a deal. You've got the formula for magnetic flux, or you've got the formula for the EMF in terms of the magnetic flux change. The hard part tends to be finding the direction. And Lenz's law comes to our rescue. It tells us that nature hates change, and it always tries to induce a field such that the change in flux is nullified. Sometimes that means increasing the field. Sometimes that means decreasing the field. It always wants to counteract the change.